Hello, good evening, everyone, and welcome to the week 7 lecture of thermodynamics tutorial. So, we'll wait for some minutes and then we'll start today's class. Okay, uh, let's start. Hello, I'm Thananka Sutia, and today I will be taking classes solving numericals. Basically, that will be helpful for you to solve the assignment number 7, which is basically related to your thermodynamic devices. Okay, once again, we may have done some of easy problems related to these devices. Now today we will do some difficult sums. Okay, so the first question is: a steam turbine receives steam at a pressure 20 bar and superheated to 88.6 degrees Celsius. The exhaust pressure is 0.07 bar. Expansion of the steam takes place isentropically, and you have to calculate the heat rejected, the heat supplied, assuming the feed pump supplies water to the boiler at 20 bar. Net work done by the turbine, thermal efficiency, and then theoretical steam consumption. Okay, so this is basically in order to do that, let us first take what is going on. If I'm considering this one as the turbine, okay, so there will be some input to the turbine. Okay, this is basically, it is saying as a steam, it is entering and it comes out of the turbine after it is getting expanded. Okay, then what happens? Then there will be cooling of this vapor to the liquid state. Okay, okay, and then what happens? There is a pump, okay, which will take some amount of work and it will again give it to its original pressure level. Okay, before that expansion takes place, and then at constant pressure there is some heat addition takes place. Okay, so this is the overall flow chart of this, whatever we are going to say here. Some work will be produced and here some work will be consumed. Okay, here some heat will be rejected and here some heat will be accepted or added. Okay, so let us and we know that this is the schematic diagram, and in order to solve such problems, one more diagram is important to us, that is our TS diagram. So if I will name this point as 1 and I will name this point as say 2, okay, I'll name this point as 3 and I will name this point as 4. Okay, so then basically if I draw the TS diagram, okay, so this is my saturation line, so these are my two pressure levels. Okay, so this is my pressure P1 and this is my pressure P2, and it's already saying that it is some at superheated level. Okay, so this is my point 1, and from here isentropically it is getting expanded, so this is my point 2. Okay, then this will be my point 3. Okay, and then once again this will be my point 4. Okay, and then this will be my point 1. Some people also wants to check how much amount of heat is because there is two amount of heat from 4 to say this 0.5, there will be sensible heating of this liquid water, and then from 5 to this point, say this 0.6, there will be latent heating, and from 6 to 1, and again there is some sensible heating. Since here we will so I'm giving just the name, you cannot identify those points here, but these points 5 and 6 are in between somewhere here. Okay, so this is the overall process here. Now what are the things that are given to us? Okay, so we are given pressure P1, okay, that is equal to your 20 bar, but we are not given I think the temperature T1. Yes, it is only saying that it is being superheated to 88 degrees Celsius. That means degree of superheat is given to us. Degree of superheat is given to us, okay, and that is your 88.6 degrees Celsius. So and then it is telling us it is expanded to 0.02 pressure, so that means your pressure P2 is given to us, that is basically your 0.07 bar. Okay, now yeah, so then whatever thing, and then the rest we have to calculate. Okay, so for that what we require we will require our steam table. Okay, so our first working pressure is that is our 20 bar. Okay, so at 20 bar, that means in our pressure table we have to go and look at our 2 megapascal, because here everything's are given in megapascal. Okay, so in the pressure chart we have to go to the, yeah, so this is our 2 megapascal. Okay, so at the point 1 we are here and it is at the 2 megapascal, and at the 2 megapascal what is our saturation temperature? So T saturation at 20 bar is equal to how much you got? 212 point approximately 4 degrees Celsius. Okay, so 212.4 degrees Celsius. Okay, so now we are given degree of superheat, that's why T1 temperature at the point 1 is what? T saturation at 20 bar plus degree of superheat. Okay, so that is basically 212.4 plus 88.6 degree Celsius. Okay, so that will be your 300 degrees Celsius. Okay, so at 300 degrees Celsius now we have to look for the various properties. Okay, so now in the steam table we have to go to the superheated table, because we have seen that the saturation temperature is 200 and our T, that is T1, is greater than this saturation temperature. That means it is a superheated steam, and question is also telling us. Okay, so we'll go to the superheated table to the 2 megapascal level. Okay, so we got to the 2 megapascal level and we have to see 300 degrees Celsius. Yeah, so this is our 300 degrees Celsius, and from here, okay, so we will take the various properties. Okay, so at 20 bar and 300 degrees Celsius, what we got? S1 we will get, yes or no? So S1 is basically 6.7684 kilojoule per kg, 6.7684 0.7684 kilojoule per kg Kelvin. Okay, and H1 we got 3024.2 3024.2 kilojoule per kg. Okay, now what we know that yeah, so we know that from this graph that from 1 to 2 it is an isentropic process. Okay, so whatever is at the point 1 it will be same at the point 2. Okay, that means entropy at the point 1 will be entropy at the point 2. Why? Because it takes place that the expansion of the steam takes place isentropically. Okay, so therefore now since steam expansion in turbine takes place isentropically, therefore my S1 will be equal to S2, and that will be nothing but 6.7684 kilojoule per kg Kelvin. Okay, now then again see here, now my S2 I can also calculate if I will look at the pressure P2 level. Okay, so at the pressure P2 that is 0.07 bar, that means 0.007 megapascal, we have to see the property that is S2. Okay, 0.007 megapascal. Okay, 0.007 megapascal, and here this is VF VG, this is UF UG, this is HFG, and this is okay, so this is SF SFG. Okay, so from here also I can calculate. Let me write it here again. At P equal to 0.07 bar, okay, my SF, what is my SF? My SF is 0.55903, 0.55903 kilojoule per kg Kelvin, and my SFG, what is my SFG? My SFG is 7.7154 kilojoule per kg Kelvin. Okay, then my HF is 163.35 kilojoule per kg, 163.35 kilojoule per kg, and my HFG is 2408.4 kilojoule per kg. Okay, so now using these two also I can calculate S2. That S2 will be what? SF at 0.07 bar plus x SFG at 0.07 bar. Okay, now then what I can do, I will just replace it 6.7684 that will be equal to 0.0.55903 plus x times 7.7154 7.7154. Okay, and from here I will get the dryness fraction at the point 2. Okay, so your x will be 6.7684 minus 0.55903 by 7.7154. Okay, so the dryness fraction I have got is 0.8. Okay, is it clear till here? So we have got the dryness fraction as 0.8. Okay, now what I can do, I can calculate H2. So H2 is basically HF at P2, I think it's P1, sorry, P2, HF at P2 plus X times HFG at P2. Okay, so what is my HF? So this will be 163.35 plus 0.8 times 2408.4 2408.4. okay, kilojoule per kg. So what you will get here, 0.8 into 2408.4 plus 163.35. okay, so that will be 2090.07 kilojoule per kg. Okay, so you got H1, you got H2. Okay, then what we have to calculate, we have to first calculate heat rejected. What is the basically the heat rejected? Heat rejected is basically, it is from 2 to 3, yes or no? So the decrease in the enthalpy in going from the process 2 to 3 is basically your heat rejected. Okay, so therefore heat rejected is equals to H2 minus H3, and this H3 is nothing but H2 minus HF at P2. okay, so H2 is 2090.07 and HF is 163.35. okay, so from here you will get 2090.7 minus 163.35, 1927.35 kilojoule per kg. okay, so we have got the first answer. Now then, since we know H1, we know H2, and from here we can also calculate one more thing. Okay, let me show you once again. I know the enthalpy at the point 1, I know the enthalpy at the point 2. So if I will subtract this H1 from H2, what you will get basically, you will get the energy change from H1 and H2. And what is the energy change from H1 and H2 is basically the work done by the turbine. Okay, so therefore work done by turbine, or that is WT, is basically your H1 minus H2. Okay, so my H1 I got was 3024.2, 3024.2, and your H2 you got as 2090.07, 2090.07. okay, 3024.2 minus 2090.07, so you'll get 934.13 kilojoule per kg. Okay, so this is the work done by the turbine. Then what will be the net work done? Okay, so net work done is what? Work done by the turbine minus the work that is required by the pump. Okay, the pump is also requiring the work. Now how to calculate pump work? I think you have already got the formula for calculating pump work is nothing but minus of V dP integration, isn't it? Okay, so that means what we will get, Vf at P2 times P1 minus P2. Okay, and I am not putting the negative sign because I have already done it here. Okay, so Vf at P2 we can calculate from the steam table, and you will get this one as 0.001. okay, and what is your P1? Your P1 is 20 and your P2 is 0.07. okay, now this is in bar, so I am converting this into kilopascal so that everything is they are in terms of kilojoule per kg. So this is basically your 1.993 kilojoule per kg. okay, so therefore net work done is 934.13 minus 1.993. okay, 934.13 minus 1.993. this is your 932.137 kilojoule per kg. okay, so what are the things we have got? We have got the heat rejected, we have got the net work done, we have got the work done by the turbine. Okay, now we need to calculate the heat supplied. okay, so since this is a cycle, we know that from first law of thermodynamics for a cycle, what we know, that summation of all the W will be equal to summation of all the Q. okay, so that will be WT minus WP, that will be basically to your Q added minus Q rejected. okay, this we have already got. WT minus WP is 932.137. okay, we have already got the heat rejected as 1927.35. so Q added minus 1927.35. so from here I'll get Q added is equal to 1927.35 plus 932.137. Okay, 1927.35 plus 932.137. Okay, so you will get here 2859.487 kilojoule per kg. Okay, so we have got 4. Now we need to define the thermal efficiency. So we know eta thermal is nothing but your output divided by input. Okay, so what is the output? Your output is basically W net, and what is your input? Your input is basically your Q added. Okay, so W net, you have calculated this one as 932.137, and your Q added, you have just got it as 2859.487. okay, 932.137 by 2859.487. okay, so your efficiency is, you will get is 0.3259, that is your 32.59%. okay, next what is left with you is the theoretical steam consumption. So in order to calculate the theoretical steam consumption, you have to just remember this formula, that the theoretical steam consumption is equal to 3600 divided by W net. Basically it is 1 by W net, but it is in multiplied by 3600 net in order to convert this into kg per kilowatt hour. okay, so we have already got W net as 932.137. so 3600 divided by 932.137 kg per kilowatt times hour, so that will be 3600 by 932.137, so it is 3.86 kg per kilowatt hour. okay, fine. If you have any doubt, you can ask me. okay, so let us move. Okay, if you have any doubt, you can take your time. okay, if you have doubt, we will discuss. So next, a piston cylinder device whose piston is resting on the top of a set of stops initially contains 0.5 kg helium gas at 100 kilopascal and 25 degrees Celsius. The mass of the piston is such that 500 kilopascal of pressure is required to raise it. How much heat must be supplied to helium before the piston starts rising? And the CV of helium at room temperature is given as 3.1156 kilojoule per kg Kelvin. Okay, fine. So what is the condition that, suppose this is a piston. okay, so this is a piston. Now this piston, it is basically resting on some stoppers. okay, so this is one stopper, and this is another stopper. Okay, this is basically resting on one stopper and basically done by force balancing. Okay, so this is resting on some stopper. Now then when it is resting, the mass of helium it's there is 0.5 kg. Okay, and the pressure is your 100 kilopascal. That is the initial state, and your temperature is 25 degrees Celsius. Okay, now the mass of the piston is such that 500 kilopascal of pressure is required to raise it. That means what? Until and unless the pressure of this inside pressure becomes 500 kilopascal, this piston will not rise. Okay, because we know that whenever we will increase pressure, okay, whenever we will increase the pressure here, so it will be it will increase the temperature, that will increase the internal energy, and as a result it will start to rise. Okay, but that pressure should be 500 kilopascal here. Okay, so in order to do that, what amount of heat you will be adding so that this will just start rising? That means your final pressure should be 500 kilopascal, and then you have to calculate how much heat should be supplied so that your this one just starts rising. That means the question is that what amount of Q should be supplied so that the pressure becomes 100 kilopascal. Okay, is it clear? So that means from 100 kilopascal to 500 kilopascal, what type of thermodynamic process is it? Can you give a guess? It will be a constant volume process. Why? Because until and unless the pressure reaches 500 kilopascal, this piston will not expand, and if this piston will not expand, the volume of this will remain the same. Okay, so until and unless from 100 kilopascal to 500 kilopascal, this is basically your constant volume process. So let us start. P1 is equals to 100 kilopascal, and T1 is 25 degrees Celsius, which I will convert. Then it will basically become 298 Kelvin, I think. Let me check. 25 plus 273. Yes, 298 Kelvin. Okay, and your P2 is 500 kilopascal. Now since it is an helium, so we can apply ideal gas process. So in ideal gas, P1 V1 by T1 is equals to P2 V2 by T2. Now going from P1 to P2, the volume will remain the same. So from here I can calculate T2 is nothing but P2 by P1 times T1. Okay, so 5 into 298 Kelvin. Okay, 1490 Kelvin. Now we know the final temperature. So in going from temperature T1 to T2, now we should just calculate what amount of heat. So first, from the first law of thermodynamics, Q is equals to delta U plus W. Now since there is no any other work, so this W will be replaced by delta U plus PdB work. Okay, now PdB work for a constant volume process is 0 because this dV term is 0. Yes or no? So that's why Q is nothing but delta U. And what is the delta U for an ideal gas? It is nothing but M CV delta T. That is basically M CV T2 minus T1. So what is your M? Your M is 0.5. Okay, and CV for helium is given to you as 3.1156 kilojoule per kg Kelvin, and your T2 you know it's 1490, and T1 is basically 298. Okay, so kilojoule per kg Kelvin, so this will be in terms of kilojoule. Okay, 0.5 into 3.1156 into 1490 minus 298. Okay, so this is your 1856.89 kilojoule. Okay, very simple question. If you have any doubt, you can ask me. Okay, fine. Let us move to the next question. A well insulated rigid tank contains 5 kg of saturated liquid vapor mixture of water at 100 kilopascal. Initially, 3/4 of the mass is in liquid phase. Then an electric resistor is placed in the tank, is connected to a 100-volt source, and a current 8 ampere flows through the resistor when the switch is turned on. Determine how long will it take to vaporize. Okay, so what happens that initially, okay, so there was a 5 kg of, I have steam plus liquid water. Okay, now after that what happens, 5 kg of steam plus liquid water, where 3/4 was liquid water. 3/4 is liquid water. Okay, so then after that what they have done, they have connected an electric some source, okay, which has got voltage 110 and current of 8 ampere was flowing. Okay, and you have to determine for how many time it will flow, so that whatever liquid was there, it became totally vapor. Okay, it became totally vapor. Okay, so you have to calculate that now. Okay, so let us start. Okay, so let us first apply the first law of thermodynamics. Q is equals to W plus delta U. Okay, now since it is told as a well insulated tank and it is called a rigid tank, okay, so that's why this insulated, this Q is equals to 0, and since in a rigid tank, so WPdV is not there. Whatever W is there is because of this external work, and we know that this an electrical work is there, then it will be your negative. Okay, electrical work is there and then delta U. Okay, so that means what we got, that whatever W electric will be there, that will be equal to your change in internal energy of the system. Okay, now for calculation of electrical work, we know one formula, that is V into I into T. Okay, and that is your delta U. Now we know V, we know I, we just have to calculate T. For doing that, we need to know what is the delta U. Okay, so now then we have to know what is the initial state of the steam and then what is the final state of the steam. Okay, so that means we have to calculate U2 and U1. Okay, so initial state of steam, initial state of steam. Okay, so for initial state of steam, what we know, the pressure is 100 kilopascal. Okay, now since the pressure is 100 kilopascal, do we know the temperature? Yes, we know the temperature because it is telling us that this is a saturated liquid vapor mixture. Okay, that means it lies in this zone. Now which zone? There will be so many zones. It will lie in the zone of the pressure that is corresponding to your 100 kilopascal, or you can say that 10 megapascal. Okay, so this will be my temperature, the T saturation, that is corresponding T saturation for 100 kilopascal. Okay, so that will be my temperature. And can anyone say what is X here? Your X1 is 1/4. Why? Because we know that 3/4 is liquid water, that means 1/4 is vapor, so X1 is 0.25. These are the informations which I know. Now from these informations, can I calculate my u1? Of course I need to just go to the steam table. Okay, so I'll go to the 10 megapascal. Okay, so 10 megapascal. So at 10 megapascal, what are the things I know? At 10 megapascal, okay, the things that I know are Vf is equal to 0.0014. So 100 kilopascal, sorry, 100 kilopascal is not 10 megapascal, it is 100 into 10 to the power 5. So this is 0.1 megapascal. I'm sorry, very sorry. So I need to go at 0.1 megapascal. Okay, so at 0.1 megapascal, your Vf is 0.001043, 0.001043 meter cube per kg. Okay, and your Vg is 1.6939, 1.6939 meter cube per kg. Okay, then uf is your 417.40, 417.40 kilojoule per kg, and your ug is 2505.5, 2505.5 kilojoule per kg. Okay, so these are the things which I know. Then I can calculate V1. Okay, that means at the initial state of the steam, that is basically Vf plus x Vfg. Okay, so put this value 0.001043 plus x is 0.25 times 1.6939 minus 0.001043. okay, you will get this as 0.42 0.42428 meter cube per kg. Okay, then next u1 similarly is nothing but uf plus x ufg. Okay, so this is your 417.40 plus 0.25 times 2505.5 minus 417.40. okay, so this will be your 2505.5 minus 417.40 plus 417.40. okay, so this one you'll get as 939.5 kilojoule per kg. okay, so I have got u1. okay, so initial state of the steam I have got. okay, whatever things I require for the calculation, I have got the initial state for the steam. okay, now Now we know that the volume of this one is not going to change. Okay, why the volume is not going to change? Because it will be it's the container and we are not changing it. Okay, so the volume will remain the same. So what we will do, this one is v2 will be equal to v1, and that is nothing but 0.42428 meter cube per kg. Okay, then now we have to go to the steam table and we need to check where this volume 0.4248 is there, what is the internal energy corresponding to that. Okay, what is the internal energy that is corresponding to 0.424 that volume. Okay, so you can see that this will basically lie between these two. Okay, these two, basically this will lie between these two, so we'll do a linear interpolation. Okay, so this volume will lie between this one, so we'll do a linear interpolation. By using linear interpolation, what will we get? We'll basically do this 0.40542, 0.40542, I'm sorry, 0.40542 minus 0.42274, 0.42274, then what we require, 0.42428 minus 0.42274, and here I will do the corresponding UG values. Okay, that is 2557.9, 2557.9 minus 2556.4, 2556.4, then this, let it be x, and this will be 2556.4, and doing this all this and then adding up this one, we will finally get this u2 value is your 2556.7 kilojoule per kg. Okay, so you'll get this one as this one kilojoule per kg. Okay, now then we will just put it in the formula. Vi delta t is basically your delta u. Okay, fine, and delta u, so vi, I have taken it as t maybe, so this will be m into u2 minus u1, is not it? So just put it here, you'll get t is equals to I think m is given as 5 kg. Okay, your u2 is 2556.7 minus your u1 is 939.5 divided by v. V is your 110 volt, and your I is 8 ampere. Okay, in doing this you'll get this time in seconds. Okay, five into 2556.7 minus 939.5 divided by V is your 110 into 8. Okay, so you will get this. Oh, this was kilojoule, no? So you have to convert this into joule. 1000. Okay, so you'll basically get this one as 919188.6 seconds. If you convert this to minute, so this will be your 153.14 minute. Okay, fine. Let us go to the next question then. Water vapor enters a nozzle at 400 degrees Celsius and 800 kilopascal with a velocity of 10 meter per second. It leaves at 300 degrees Celsius and 200 kilopascal. During this process, heat is lost at the rate of 25 kilojoule per second for an inlet area of 800 centimeter square. Determine the velocity and volumetric flow rate at the nozzle exit. Okay, so this is how a nozzle looks. Okay, so this is the entry point and say this is the exit point. Okay, so what we are given that T1 is equal to 400 degrees Celsius, and then P1 is given as 800 kilopascal, then velocity is given to us at this point is 10 meters per second. Okay, then it leaves at 300 degrees Celsius, so T2 is given to us as 300 degrees Celsius, then P2 is given to us at 200 kilopascal. Okay, and in this process there is a heat loss. I will write this as minus because we know that heat loss from the system is negative kilojoule per second. This is basically kilowatt. Okay, and then inlet area is also given to us. The inlet area is 800 centimeter square. So if you convert this to meter, 800 into 10 raised to the power minus 4, so this will be 0.08 meter square. Okay, so these are the things that are given to us. Okay, fine. Now see, this is an open flow process, so we know that for open flow process the formulas are, so dmcv by dt is basically your inlet minus outflow of mass. Now since this is considering this as steady flow, we'll get m1 dot is basically equals to m2 dot, so that means the entry mass flow rate and the exit mass flow rate are the same. The next, the energy balance DECV by dt will be basically equal to q dot minus w dot plus m1 dot h1 plus v1 squared by 2 plus z1 minus m2 dot times h2 plus v2 squared by 2 plus z2. Okay, so again considering this a steady flow, so this will be 0, and since no work is given to us, this term will be 0. Okay, now again nothing is said about the change in kinetic and so then let us put this is 0 and this is q dot, and we know that m1 dot and m2 dot are same, so this will be basically m dot times h1 minus h2 plus v1 squared minus v2 squared by 2 plus z of z1 minus z2. Okay, now the change in potential energy also we can neglect, yes or no, because nothing is said to about us. So what we are getting, we are left with these things. Okay, and from this we can calculate the velocity at the exit point. Okay, now for that we need to have H1, we need to have H2, we need to have V1 which is already given to us, and we also need to have m dot. Now how will we get H1 and H2? Now see, this is a water vapor. Okay, and water vapor, and it is telling us that it is at 400 degrees Celsius and 800 kilopascal. So we will go to the steam table and we'll first check what is the condition of the steam at this state. Okay, so at 800 kilopascal, that means at your 800 into 10, so 0.8 megapascal. Okay, so at 0.8 megapascal, what is the scenario? At 0.8 megapascal, the saturation temperature is 170.4 degrees Celsius, and here our temperature is given to us as 400 degrees Celsius. So we have to go to the superheated table. Okay, let us also check at 300 at 200 megapascal also. That means at 0.4 megapascal also we need to check. So that yeah, at 0.4 it is 143, and here it is also greater than this one. So both are at superheated state. Okay, so 400 degrees Celsius, 800 kilopascal. First of all we'll check. Okay, no, at first we'll get this point now. So 300 degrees Celsius, 200 kilopascal, that means 0.2. Yeah, so 0.2 megapascal and 300 degrees Celsius, this one. Okay, this is the point, and here we need H, so that H is 3072.1. okay, so what we got from steam table, we got H2 is equal to your 3072.1 kilojoule per kg. Okay, and what will be H1? H1 we need to check at 0.8 megapascal, isn't it? Okay, we need to check at 0.8 megapascal. Yes, 0.5, 0.6, 0.7, yes, 0.8 megapascal and 400 degrees Celsius. So this is the point, and here the H is 3267.6, 3267.6 kilojoule per kg. Okay, so I have got H1, I have got H2. I need to calculate V2, but for that I need to know m dot. So m dot is also equal to m1 dot, and m dot is also equal to m2 dot. Okay, now m dot. Okay, so m dot, we know that it is equal to m1 dot, which is equals to what? Rho 1 a1 v1. Okay, it is also equal to m2 dot, and that is equal to your rho 2 a2 v2. But in the question we are not given, we are given we have to calculate v2, so we cannot go by this process. And the other thing is that our a2 is not given to us. Okay, only a1 is given to us, so that's why we will go by rho 1 a1 v1. Okay, now again, rho 1, is it given to us? But yes, from the steam table we can check this one as basically the inverse of the volume 1. Okay, so from the steam table we also need to check what is your v1. Okay, so the v1 will be it is basically 0.38428 meter cube per kg. Okay, So your A1 is 0.08 and your V1 velocity is given as 10 meter per second, and this volume at the initial point is 0.38428, 0.38428. okay, 0.08 into 10 by 0.38428, 2.08 kg per second. So we'll put all these things in this equation. Okay, so Q is given as minus 25. Okay, so 0 is equals to minus 25, basically it is in kilowatt. Okay, then m dot, what is your m dot? 2.08. okay, h1 minus h2, your h1 is 3267.6, 3267.6 minus your h1 is 3072.1, 3072.1 plus v1 squared minus v2 squared. Okay, what is v1? v1 is 10 meter per second. v1 squared minus v2 squared I need to calculate, divided by 2, but now I will multiply with 1000 because this is in kilojoule, so this should also be in kilojoule. Okay, then only you'll get the answer. Okay, now I'll move this one that side. So this will be basically 25 by 2.08, and this one I can do 3267.1 minus 3072.1, 195.5, 195.5 plus 100 minus v2 squared by 2000. Okay, so this will be what? v2 squared minus 100 is basically your 195.5 minus 25 by 2.08 into 2000. So this is your 366.96 into 10 to the power 3. Okay, then your v2 squared will be plus 100, so 367.06 into 10 to the power 3, so that means your v2 will be root over this one. Okay, six 5.85 meter per second. Okay, so this is my velocity x the exit. Okay, then what is the volumetric flow rate at the exit then? Therefore volumetric flow at exit, this is basically your v2 dot, that is nothing but m dot times v2, yes or no, kg per second into meter cube per kg. So at v2 from the steam table I know m dot is what? I have calculated the m dot as 2.08, and from steam table I can calculate v2. Okay, that is your 300 degrees Celsius, 200 kilopascal, that means 0.2 megapascal. 0.2 megapascal 300, so the volume is 1.3162. okay, 1.3162. okay, 2.08 into 1.3162, you will get this as 2.737 meter cube per kg. okay, so this is the answer. Next, air enters an insulated turbine at 1600 kilopascal and 450 degrees Celsius with a velocity of 55 meter per second and leaves at 150 kilopascal with a velocity of 150 meter per second. The inlet area of the turbine is 60 centimeters square. Then if the power output to the turbine is 190 kilowatt, determine the exit temperature. okay, so similarly this is how a turbine looks. okay, this is the entry point and this is your exit point. okay, now work done by the turbine is given to us, and then it is said that this is an insulated, so that means your Q will be 0. okay, once again if I will do steady flow process, so I will get m1 dot is basically equals to m2 dot, and that is basically equals to your m dot. Let us see what are the things that are given. P1 is given at 1600 kilopascal. okay, 1600 so this is basically a 1.6 megapascal. Then T1 is given as 450 degrees Celsius. okay, V1 is given as 55 meters per second, and then 55 meters per second, and then inlet area is given A1 is equals to 60 centimeters square, which is equals to 16 to 10 raised to the power minus 4, so that will be 6 into 10 to the power minus 3 meters square. okay, and then your exit leaves the pressure at 150 kilopascal, so P2 is given as 150 kilopascal, which is basically your 0.15 megapascal. okay, and then V2 is given to you as 150 meters per second. So you have to determine the exit temperature, and WT is given to you as 190 kilowatt. okay, so we have already got this from the conservation of mass. Then from the conservation of energy we will get again dECV by dt will be equal to Q dot minus W dot plus M dot H1 minus H2 plus V1 squared minus V2 squared divided by 2 plus Z of Z1 minus Z2. okay, once again this is a steady flow, gone. Adiabatic or insulated it's given, so this is gone, and change in potential energy is gone. okay, so from here what is left behind is that W dot is nothing but M dot times H1 minus H2 plus V1 squared minus V2 squared by 2. okay, so now this is air, so we cannot go into the steam table and look. So whatever we should we need, these all things should be calculated by some other means. okay, so W I will put here. So how to calculate H1 and H2? Now we know that for an ideal gas, okay, H is nothing but CPT, so this I can further write this one as M dot Cp T1 minus T2, okay, plus V1 squared minus V2 squared by 2. Is it okay till here? Now do I know T1? Yes. Do I know T2? No. I need to calculate T2. Do I know V1? Yes. Do I know V2? Yes. So this one I know, this one I know, this one I know. I know Cp of air, I know W. Now one more thing is left with us is M dot. okay, now Now how will we calculate m dot? M dot is basically your m1 dot is basically your rho 1 a1 v1. Okay, so I know a1, I know v1. How will I calculate rho 1? Okay, so since this is air, I can apply ideal gas equation P equals to rho RT. Okay, so if P equals to rho RT, then rho will be equal to your P by RT. Okay, so from here I can calculate P1 by RT1 times A1 V1. This is my mass flow rate. Okay, so what is my P1? My P1 is 1600 kilopascal. 1600 kilopascal. Okay, so my P1 is 1600 kilopascal. And then R is 0.287 kilojoule per kg Kelvin, which I know. And then T1 is 450 degrees Celsius now. So this will be 450 plus 273 723. What is your A1? Your A1 is 6 into 10 to the power minus 3 as far as I remember. Yes, 6 into 10 to the power minus 3. And your this one is 150 meters per, no, it's a 55 meter per second. 55. Okay, so from here you will get m dot. Okay, 1600 into 6 into 10 raised to the power minus 3 to 55 by 0.287 into 723. So this will be your 2.54 kg per second. Okay, so now in this equation I know everything, I just need to put here. Okay, so what is my W dot? 190. Therefore 190, this is in kilowatt, remember. Okay, 190 is equals to your m dot. M dot is equals to 2.54. Okay, now CP is 1.001 kilojoule per kg Kelvin. What is your T1? T1 is in degree Celsius, so it's 450. Okay, and I need to calculate T2. Okay, plus V1 squared, that is 55, minus V2 squared. What is my V2 squared? It is 150 meters per second by 2 into 1000. Why? Because it is in joule, so I need to convert everything in kilojoule. Okay, now 190, this will be 73.93 is equals to 1.001 into 450 minus T2, and this will be squared minus 150 squared by 2000 minus 9.7375. okay, so 450 minus T2 will be basically equal to 73.93 plus 9.7375 divided by 1.001. okay, 73.93 plus 9.7375 divided by 1.001. so this is your 83.58. okay, so from here your T2 is 450 minus, and so this is your 366.4 degree Celsius. okay, now air enters an insulated diffuser operating at a steady state with a pressure or 0.65 bar, temperature 67 degrees Celsius, and velocity 300 meter per second, and the inlet area is 0.5 meter square. At the exit, the pressure is 1 bar, the area is 0.6 meter square. Potential energy changes are neglected. So what is the mass flow rate and the temperature of the air at the exit? Okay, so again, once again, the same type of pattern, but just the devices are different. So this is a diffuser, which is again insulated diffuser. That means the Q is 0. Okay, now this is the entry point and this is the exit point. Okay, so your P1 is 0.65 bar, that is 0.065 megapascal. Okay, then T1 is your 67 degrees Celsius, and V1 is your 300 meters per second. Then inlet area A1 is your 0.5 meter square. Okay, then your exit pressure is 1 bar. Okay, and your exit area is 0.6 meter square. Okay, now if you apply steady state, once again this will be m1 dot will be equal to m2 dot, and that will be equal to m dot. Okay, now again dEcV by dt is equals to q dot minus w dot plus m dot times h1 minus h2 plus v1 squared minus v2 squared by 2 plus z of z1 minus z2. Now they are already saying that kinetic energy, potential energy changes are 0, steady state this is 0, insulated this is 0, no work is given, and diffuser normally does not do any types of work, so this is also equal to 0. So what is left with us is that m dot times h1 minus h2 plus v1 squared minus v2 squared divided by 2 is equal to your 0. So from here what I can write here is that h1 minus h2 is equals to v2 squared minus v1 squared divided by 2. Okay, now if this is in meter per second, so this will be basically equal to 2000. Yes or no? Then this will be what? 2000 into h1 minus h2 is your v2 squared minus v1 squared. Okay, clear? Oh, so I need to calculate temperature at the exit. Also from here I can do this one. Okay, I should not do this because basically I require this one. So h2 minus h1 will be v1 squared minus v2 squared divided by 2000. So my h2 will be equal to h1 plus v1 squared minus v2 squared by 2000. Okay, then from here h2 is nothing but Cp times T2y because it is an ideal gas. So Cp times T1 plus v1 squared minus v2 squared, v1 squared minus v2 squared by 2000. Okay, so from here T2 is nothing but T1 plus v1 squared minus v2 squared divided by 2000 into Cp. Okay, so what is my T1? Hello, yeah, so what is my T1? My T1 is basically 67 degrees Celsius plus v1 squared minus v2 squared. So v1 is 300 meter per second but I don't know V2 square, correct now? So what I know, since mass flow rate remains the same, so rho 1 A1 V1 will be equal to rho 2 A2 V2, isn't it? Okay, rho 1 A1 V1, that will be equal to rho 2 A2 V2. Fine. Then what will be your rho 1? P1 by R T1 A1 V1, and this will be P2 by R T2 times A2 V2, and from here R got cancelled, so V2 is nothing but P1 by P2 into T2 by T1 into A1 by A2 into V1. Okay, now you just have to put it here. You know V1 square is nothing but 300 square. Okay, and then you will put this V2 value here. Okay, because here itself it contains T2, isn't it? Here itself it contains T2. The all other you will multiply it here. Okay, say P1 by P2. What is P1 by P2? 0.65 by 1, so that is 0.65. T1 I will keep it as is this, that is 67 plus 273, 310 into T2 into A1 by A2. Okay, so A1 by A2, A1 is 0.5, A2 is 0.6, so that is 5 by 6, and V1 is given as 300. Okay, so from here what you can do, 0.65 into 5 into 300 by 6 into 310, 0.524 T2. Okay, so here you will getting 0.524 T2, so this will be basically 0.524 T2 whole square divided by 2000 into 1.001. Okay, so solving this, what you will get here, T2 will get approximately equal to 355 Kelvin. Okay, fine. Next, the temperature and pressure of air in a large reservoir are 400 Kelvin and 3 bar respectively. Okay, and a converging diverging nozzle area of 0.005 meter square is fitted to the wall of the reservoir. The static pressure of air at the exit section for isentropic flow through the nozzle is 50 kilopascal. The characteristic gas constant and the ratio of the specific heats are this one and this one. Determine the density of the air at the nozzle exit and the mass flow rate of the air. Okay, so suppose this is a tank. Okay, and then there it is connected, at somewhere it is connected a converging diverging nozzle. So a converging diverging nozzle is connected here. Okay, so the temperature and pressure at this tank is what? 400 Kelvin and 3 bar. Okay, converging diverging nozzle with an exit area of 0.005 meter square is attached to it. Okay, so if this point is the point 2, so the area of the exit is 0.005 meter square. Okay, static pressure at the exit section through it P2, it is basically equal to 50 kilopascal. Okay, characteristic gas constant is given, so density at the nozzle exit you have to calculate. Now since this is a what you call converging diverging nozzle with an isentropic flow, so this entire process is reversible adiabatic process. Okay, and for reversible adiabatic process, what we know that T2 by T1 is equals to P2 by P1 to the power gamma minus 1 divided by gamma. Okay, so from here what we will get, T2 is equals to T1 times P2 by P1 by into gamma minus 1 divided by gamma. What is your T1? T1 is 400 Kelvin. What is your P2? P2 is 50 kilopascal. And your P1 is 30 kilopascal. Yes or no? 3 bar, that means 30 kilopascal. So gamma minus 1, 0.4 divided by gamma. Okay, 400 into 5 by 3 to the power 0.4. So that is your 462.85 Kelvin. Okay, now then you know T2, you know P2, so from that therefore density rho 2 is nothing but P2 by RT2. So you know P2 50, okay, you know 0.287, and this will be 462.85. okay, 50 by 0.287 into 462.85. so your answer is 0.727 kg per meter cube. Okay, then next you have to calculate the mass flow rate at the exit. So what will be the mass flow rate? Basically m dot is nothing but rho 2 A2 V2, is not it? So you know the exit area A2. Now you have to calculate the velocity at the exit. Okay, so how will you calculate the velocity at the exit then? Simple, we have already done. Such calculations. So dE by dt is equals to q dot minus w dot plus m dot h1 minus h2 plus v1 squared minus v2 squared by 2 plus z of z1 minus z2. okay, neglecting the kinetic and the potential energy changes to be 0. This one is not there, this one is not there, and also this one is not there. You will get basically h1 minus h2 is equals to v2 squared minus v1 squared by 2. Now since the inlet area is much larger, so inlet velocity can be compared as 0 in comparison to this one, so this will nothing be equal to 2 times of h1 minus h2 is equal to your v2 root over. Okay, and so now since this is an ideal gas, so that will be 2 into Cp into T1 minus T2 is basically equal to your V2. Okay, so what is your T1? Your T1 is 400 Kelvin and your T2 is 462.85 Kelvin. You have to also put 1000 here because this was in joule. So what you will get here, 2 into 1000 into T1 minus T2, that is your 462.85 minus 462. Okay, so V2 is your 354.54 meters per second. Now from here you just put it here, rho 2 A2 V2 m dot is equals to rho 2 A2 V2. So rho 2 I got 0.727 into area is given as 0.005 and V2 is given as 354.54. okay, so that will be your 1.28 kg per second. Okay, next, consider a vessel containing steam at 180 degrees Celsius. Okay, the initial steam quality is 0.5 and initial volume of the vessel is 1 meter cube. The vessel loses heat at a constant rate under isobaric conditions, so that the quality of the steam that becomes is equals to your so that the vessel loses heat so 0.1 in 10 hours. So find the rate of heat loss. Okay, so what you are getting here, vessel containing steam at 100 degrees Celsius. Okay, so your state temperature 1 is your 180 degree Celsius. Okay, and your initial quality of the steam is your 0.5, correct. Then initial volume of the vessel is your 1 meter cube. Okay, the vessel loses heat at a constant rate. Now from here we can calculate H1, that will be HF at 180 degrees Celsius plus X1 times HFG at 180 degrees Celsius. If you go to the steam table and do these calculations, you will get your answer as 1770.15 kilojoule per kg. Okay, similarly H2 will be what? H2 will be, how can we calculate H2? Because it is telling us that the steam okay, so now it will remain at constant pressure condition. Now what will be the constant pressure? The pressure will be basically your P saturation, P constant will be equal to your P saturation at 180 degrees Celsius. Okay, and that is basically equal to your 1 megapascal. Okay, so then at H2 our steam quality we know 0.1, so that is equal to HF at 1 megapascal plus X2 times your HFG at 1 megapascal. Okay, so putting this, you will get this one as 963.98 kilojoule per kg. Okay, now therefore heat loss is equals to your H1 minus H2 and if you do this you will get this as 806 point 806.17 kilojoule per kg. Now this is heat loss, but you have to calculate the rate of heat loss, and for that you have to multiply this one with m dot. Now how will you calculate the m dot? Okay, now you know the time, you already know the time, so you just need to know the mass and then you will divide this by time. Okay, now how to calculate mass? We know V1 is nothing but Vf at 180 degrees Celsius plus V x1 times Vfg at 180 degree Celsius. Okay, so if you put this you will get your values as 0.097487 meter cube per kg. Okay, now what we know is that this V1 is nothing but the total volume divided by the mass. Okay, so then mass will be equal to total volume divided by V1, and what is the total volume? 1, so that will be 1 divided by V1, and which is nothing but 10.258 kg. Okay, okay, then next is what? Rate of heat loss. Rate of heat loss, that is nothing but 806.17 times 10.258. so this is basically h1 m dot, and your time is given as 10 hours. Okay, so you will get in kilojoule per hour. So what will be your answer? 826.96 kilojoule per hour. Okay, fine. Let us go to the next question then. A vertical cylinder with freely floating piston contains 0.1 kg of air at 1.2 bar and a small electrical resistor. The resistor is connected to a wired external battery source. Now when a current of 1.5 amperes pass through the resistor for 90 seconds, the piston sweeps a volume of 0.01 meter cube. Assume the piston and the cylinder are insulated and air behaves as an ideal gas. Find the rise in temperature. Okay, so what is the condition is given? That a vertical piston cylinder arrangement is given. Okay, so this is the piston. Okay, and this mass of 0.1 kg contains, okay, of air. Fine, and then there is an electric resistor that is connected, okay, with an external voltage of 12 volt and a current of 1.5 ampere is passing through it. Okay, the resistor is connected, and this piston sweeps a volume. There is the delta V is given to us as 0.01 meter cube. Now you have to calculate what is the delta T, what is the rise in temperature. Okay, so again, what are the things are given? P is given as 1.2 bar. Inside this P is given as 1.2 bar. Okay, so electrical work done, delta W electrical is what? VIT, yes or no? So V is your 12, I is 1.5, and for what time it is running? For 90 seconds. Okay, so doing this you will get 12 into 1.5 into 90, so that is 1620 joule. Okay, electrical work done is given. Now first law of thermodynamics, dq is equals to delta W plus delta U plus dW. Okay, now what it is telling us, that the piston and the cylinder are insulated, so that means this thing is 0. Okay, so delta U will be nothing but delta W, so this will be 0. Now for an ideal gas, why for an ideal gas? This is an air, so this will be basically mCV delta T. Now no any other work is present, only electrical work will be present. So W electrical. Okay, now we will put here negative sign because this is work done on the system. So from here we will get here 1620 is equals to your M. What is your M? 0.1. CV is given as 700, and this will give you your delta T. So from here your delta T is nothing but 1620 divided by 0.1 into 700. Okay, $23 point. Oh, sorry, one more work is given, not W. PdV work is also given, WPdV. Okay, so sorry for that. Okay, so that will be your 0, that is equals to 0.1 into 700 into delta T, and minus W electrical is 1620, and what will be a PdV work? Pressure is 1.2 bar, that means 1.2 into 10 to the power 5 into swept volume is what? 0.01. Okay, so putting all this, you will get delta T is equals to 1620 minus 1.2 into 10 to the power 5 into 0.01. Okay, that is 420 divided by 700 into 0.1. So delta T is basically your 6 degree Celsius. Okay, next, a spherical balloon is filled with 3536 pi meter cube of helium gas. If a leak in the balloon causes the gas to escape at the rate of 70 pi meter cube per minute, then what is the rate at which radius of the balloon decreases? 50 minutes after the leakage began. Okay, so what we know that volume of a sphere is equals to V is equals to 4 by 3 pi r cube. Okay, so therefore dV by dt will be what? dV by dt, if you do, then you will get this as 4 pi r square dr by dt. Now what we require? We require the rate at which the radius is decreasing after the time t 50 minutes has passed. Okay, and now for that what you require? You require the r after 50 minutes has gone. Okay, so what it is given to us, that dV by dt is your minus 70 pi meter cubes per minute. Okay, so, and what we know, that at t equals to 0, V equals to what? This field volume 3536 pi, isn't it? Okay, time t equals to 0. Oh, so now if we will do integration, now this one dV by dt, so what we will get here? V is equals to minus 70 pi t plus c. Okay, so at times t equals to 0, if I will put here, then this V is equals to 356. So basically C is your V naught. Okay, C is your V naught. So therefore your volume equation is nothing but 3536 pi minus 70 pi t. Okay, is it clear till here? Okay, then after this what we got, V is equals to 3536 pi minus 70 pi t. So after 50 minutes what happens? Volume, therefore volume after 50 minutes will be what? This will be equal to 3536 pi minus 70 into 50 pi, that will be 36 pi meter cube. Okay, so now again that means we can calculate the radius. So 4 by 3 pi r at 50 minutes, yes or no, cube will be equal to 36 pi meter cube. So I am cancelling this pi, so from here I will get r at 50 minutes is equals to what? 3 meter. Okay, now initially we have got one equation that dv by dt is equal to 4 pi r square, 4 pi r 4 pi r square times dr by dt. So we need to calculate the rate at which radius is changing. So dr by dt is nothing but 1 by 4 pi r square times dv by dt. We know the value of dv by dt, we know the radius after 50, this one what you call, we know the radius after 50 minutes. So that will be 1 by 4 pi into 3 square into dv by dt is your minus 70 pi. So I will put this, all this, and I will get this answer as minus 35 by 18. Okay, fine. Okay, so I had 2-3 more questions, but I will give you some time if you have any doubt, and I will be wrapping up today's class. Okay, since you have no any doubt, we can conclude this class. Okay, fine. Thank you.